In mathematics, the real projective plane is an example of a compact non-orientable two-dimensional manifold, that is, a one-sided surface. It cannot be embedded in standard three-dimensional space without intersecting itself. It has basic applications to geometry, since the common construction of the real projective plane is as the space of lines in R3 passing through the origin. The plane is also often described topologically, in terms of a construction based on the Mobius strip. If one could glue the edge of the Mobius strip to itself in the correct direction, one would obtain the projective plane. Equivalently, gluing a disk along the boundary of the Mobius strip gives the projective plane. Topologically, it has Euler characteristic 1, hence a demogenous of 1. Since the Mobius strip, in turn, can be constructed from a square by gluing two of its sides together, the real projective plane can thus be represented as a unit square with its sides identified by the following equivalence relations: tilde for 0 y1 and tilde for 0 x1, as in the leftmost diagram on the right. Examples. Projective geometry is not necessarily concerned with curvature, and the real projective plane may be twisted up and placed in the Euclidean plane or 3 space in many different ways. Some of the more important examples are described below. The projective plane cannot be embedded in three-dimensional Euclidean space. The proof that the projective plane does not embed in three-dimensional Euclidean space goes like this. Assuming that it does embed, it would bound a compact region in three-dimensional Euclidean space by the generalized Jordan curve theorem. The outward-pointing unit normal vector field would then give an orientation of the boundary manifold. But the boundary manifold would be the projective plane, which is not orientable. This is a contradiction, and so our assumption that it does embed must have been false. The projective sphere: consider a sphere, and let the great circles of the sphere be lines, and let pairs of antipodal points be points. It is easy to check that this system obeys the axioms required of a projective plane. Any pair of distinct great circles meet at a pair of antipodal points, and any two distinct pairs of antipodal points lie on a single great circle. If we identify each point on the sphere with its antipodal point, then we get a representation of the real projective plane in which the points of the projective plane really are points. This means that the projective plane is the quotient space of the sphere obtained by partitioning the sphere into equivalence classes under the equivalence relation tilde, where x tilde y if y equals minus x. This quotient space of the sphere is homeomorphic with the collection of all lines passing through the origin in R3. The quotient map from the sphere onto the real projective plane is in fact a two-sheeted covering map. It follows that the fundamental group of the real projective plane is the cyclic group of order 2, i.e., integers modulo 2. One can take the loop ab from the figure above to be the generator. The projective hemisphere, because the sphere covers the real projective plane twice. The plane may be represented as a closed hemisphere around whose rim opposite points are similarly identified. Boy's surface, an immersion. The projective plane can be immersed in 3 space. Boy's surface is an example of an immersion. Polyhedral examples must have at least 9 faces. Roman surface. Steiner's Roman surface is a more degenerate map of the projective plane into 3 space, containing a cross-cap. A polyhedral representation is the tetrahemahexahedron, which has the same general form as Steiner's Roman surface, shown to the right. Hemipolyhedra looking in the opposite direction. Certain abstract regular polytopes, hemicube, hemidodecahedron, and hemiicosahedron, can be constructed as regular figures in the projective plane. See also projective polyhedra. Planar projections. Various planar projections or mappings of the projective plane have been described. In 1874, Klein described the mapping central projection of the projective hemisphere onto a plane yields the usual infinite projective plane, described below. Cross-cap disk. A closed surface is obtained by gluing a disk to a cross-cap. This surface can be represented parametrically by the following equations. where both u and v range from 0 to 2 pi. These equations are similar to those of a torus. Figure 1 shows a closed cross-cap disk. A cross-cap disk has a plane of symmetry which passes through its line segment of double points. In Figure 1, the cross-cap disk is seen from above its plane of symmetry z equals 0, but it would look the same if seen from below. A cross-cap disk can be sliced open along its plane of symmetry, while making sure not to cut along any of its double points. The result is shown in Figure 2. Once this exception is made, it will be seen that the sliced cross-cap disk is homeomorphic to a self-intersecting disk, as shown in Figure 3. The self-intersecting disk is homeomorphic to an ordinary disk. The parametric equations of the self-intersecting disk are, where u ranges from 0 to 2 pi and v ranges from 0 to 1. Projecting the self-intersecting disk onto the plane of symmetry which passes only through the double points. The result is an ordinary disk which repeats itself. The plane z equals 0 cuts the self-intersecting disk into a pair of disks which are mirror reflections of each other. The disks have centers at the origin. Now consider the rims of the disks. The points on the rim of the self-intersecting disk come in pairs which are reflections of each other with respect to the plane z equals 0. A cross-cap disk is formed by identifying these pairs of points, making them equivalent to each other. This means that a point with parameters and coordinates is identified with the point whose coordinates are. But this means that pairs of opposite points on the rim of the ordinary disk are identified with each other. This is how a real projective plane is formed out of a disk. Therefore, the surface shown in Figure 1 is topologically equivalent to the real projective plane RP2. Homogeneous coordinates. The points in the plane can be represented by homogeneous coordinates. A point has homogeneous coordinates x, y, z, where the coordinates x, y, z, and tx, tie, tz, are considered to represent the same point for all non-zero values of t. The points with coordinates x, y, 1 are the usual real plane, called the finite part of the projective plane, and points with coordinates x, y, 0, called points at infinity or ideal points, constitute a line called the line at infinity. The lines in the plane can also be represented by homogeneous coordinates. A projective line corresponding to the plane x plus by plus c z equals 0 in R3 has the homogeneous coordinates. Thus, these coordinates have the equivalence relation equals for all non-zero values of d. Hence, a different equation of the same line x plus dby plus dcz equals 0 gives the same homogeneous coordinates. A point x, y, z lies on a line if x plus by plus c z equals 0. Therefore, lines with coordinates where a, b are not both 0 correspond to the lines in the usual real plane, because they contain points that are not at infinity. The line with coordinates is the line at infinity, since the only points on it are those with z equals 0. Points, lines, and planes. A line in P2 can be represented by the equation x plus by plus c z equals 0. If we treat a, b, and c as the column vector and x, y, z as the column vector x, then the equation above can be written in matrix form as xt equals 0 or tx equals 0. Using vector notation we may instead write x equals 0 or x equals 0. The equation k equals 0 sweeps out a plane that goes through 0 in R3 and k sweeps out a line, again going through 0. The plane and line are linear subspaces in R3, which always go through 0. Ideal points in P2. The equation of a line is x plus by plus c equals 0, and this equation can represent a line on any plane parallel to the x, y plane by multiplying the equation by k. If z equals 1 we have a normalized homogeneous coordinate. All points that have z equals 1 create a plane. Let's pretend we are looking at that plane and there are two parallel lines drawn on the plane. From where we are standing, we can see only so much of the plane, which we represent as the area outlined in red in the diagram. If we walk away from the plane along the z-axis, we can see more of the plane. In our field of view, original points have moved. We can reflect this movement by dividing the homogeneous coordinate by a constant. In the image to the right we have divided by 2, so the z value now becomes 0.5. If we walk far enough away, what we are looking at becomes a point in the distance. As we walk away, we see more and more of the parallel lines. The lines will meet at a line at infinity. Lines on the plane when z equals 0 are ideal points. The plane at z equals 0 is the line at infinity. The homogeneous point is where all the real points go when you're looking at the plane from an infinite distance. A line on the z equals 0 plane is where parallel lines intersect. Duality in the equation xt equals 0. There are two column vectors. You can keep either constant and vary the other. If we keep the point x constant and vary the coefficients, we create new lines that go through the point. If we keep the coefficients constant and vary the points that satisfy the equation, we create a line. We look upon x as a point, because the axes we are using are x, y, and z. If we instead plotted the coefficients using axis marked A, B, C, points would become lines and lines would become points. If you prove something with the data plotted on axis marked x, y, and z, the same argument can be used for the data plotted on axis marked A, B, and C. That is duality. Lines joining points and intersection of lines. The equation xt equals 0 calculates the inner product of two column vectors. The inner product of two vectors is 0 if the vectors are orthogonal. In P2, the line between the points x1 and x2 may be represented as a column vector that satisfies the equations x1t equals 0 and x2t equals 0. Or in other words, a column vector that is orthogonal to x1 and x2. The cross product will find such a vector. The line joining two points has homogeneous coordinates given by the equation x1 times x2. The intersection of two lines may be found in the same way, using duality, as the cross product of the vectors representing the lines 1 times 2, embedding into four-dimensional space. The projective plane embeds into four-dimensional Euclidean space. The real projective plane P2 is the quotient of the two-sphere S2 equals R3, x2 plus y2 plus z2 equals 1, by the antipodal relation tilde. Consider the function R3, R4 given by. This map restricts to a map whose domain is S2, and since each component is a homogeneous polynomial of even degree, it takes the same values in R4 on each of any two antipodal points on S2. This yields a map P2R4. Moreover, this map is an embedding. Notice that this embedding admits a projection into R3, which is the Roman surface. Higher non-orientable surfaces. By gluing together projective planes successively, we get non-orientable surfaces of higher dimensions. The gluing process consists of cutting out a little disk from each surface and identifying the boundary circles. Gluing two projective planes creates the Klein bottle. The article on the fundamental polygon describes the higher non-orientable surfaces.